In this set of notes, we're going to take a look at logistic regression. Binary outcomes are quite common in medicine and in public health. So for example, alive, dead, diseased, healthy, infected, not infected, case control. The claim that these outcomes follow a normal distribution is clearly wrong. The binomial, or more specifically a Bernoulli distribution, is much more natural. In this set of notes, we're going to introduce logistic regression, which can be utilized to model binary outcomes. So logistic regression models a relationship between predictor variables and a categorical response variable. For example, we could use logistic regression to model the relationship between an exposure and a specific disease or health-related outcome. So logistic regression helps us estimate a probability of falling into a certain level of a categorical response given a set of predictors. We can choose from three types of logistic regression depending on the nature of the categorical response variable. There's binary logistic regression, and that's used when the response is binary. In other words, it only has two potential outcomes. Nominal logistic regression is used when there are three or more categories with no natural ordering to the levels. And ordinal is used when there are three or more categories with a natural ordering to the levels. So to start out with, we're going to start by focusing on binary logistic regression. So let's first look at how to set up the GLM. Recall that the binomial distribution is utilized to model binary outcomes like coin flip. Here, the binary outcomes could be disease, survival, infection, etc. The difference, however, is that we're not assuming that each person's coin has the same probability of landing on heads. The probability that each person will die, succumb to disease, get infected, varies depending on the explanatory variable in a way that is explicitly modeled by the GLM. So here, our random component is going to be that the response is distributed binomial, where the number of trials is equal to 1 and the probability of success is pi I. So notice that this is really the same thing as a Bernoulli distribution with probability of success pi I in this case. And then the systematic component is going to be exactly what we've seen before, and the systematic component is going to control where our explanatory variables are. So what about the link? Recall from Module 4.2, the canonical link for the binomial distribution is as follows. The first function is called the logit of pi I, and the generalized linear model based on this link is called logistic regression. So suppose that we have a single explanatory variable. So in this case, our systematic component will only consist of the intercept and the coefficient for that explanatory variable. The logistic regression is then modeled or given by the following. And then equivocally, we can write the logit or log odds as this relationship here. So how can we interpret beta 1? So notice the following. The sign of beta 1 is going to determine if pi I is increasing or decreasing as x increases. The rate of climb or descent increases or decreases as the absolute value of beta 1 increases. And as beta 1 goes to 0, the curve is going to flatten to a horizontal straight line. So if we exponentiate both sides, we have the following. So in other words, the odds are going to be an exponential function of x, and we see that right here. This provides a basic interpretation for the magnitude of beta 1. So remember that when we looked at beta 1 for simple linear regression, we would typically interpret it as something along the lines as x increases by 1, this is what we expect on average to happen. So we can do something very similar to here. So the odds multiply by e to the beta 1 for every 1 unit increase in an x. In other words, beta 1 is the odds ratio, the odds at x equals x plus 1 divided by the odds at x equals x. So to see this, what we can do is we start out with this piece right here, but let's increase x by 1. And so notice that would give this right here. So then if we perform a little algebra, notice what we end up here are two different pieces. We have our original piece multiplied by e to the beta 1, which is exactly what we were saying there. Okay, so let's look at an example. So in this section, we're going to consider a motivating example. We're going to fit a model and interpret that output. So we're going to consider a data set which involves the survival of members of the Donner Party. In the spring of 1846, a group of American pioneers set out for California. However, they suffered a series of setbacks and did not arrive at the Sierra Nevada mountains until October. While crossing the mountains, they became trapped by an early snowfall and had to spend the winter there. Conditions were harsh, food supplies ran low, and 40 of the 87 members of the Donner Party died before they were finally rescued. The data contains the following variables: age, sex, and status, which is either died or survived. And in this case, status is going to be our response variable, and we can consider age and sex as explanatory variables. So to start out with, we're going to fit a model where age is the only explanatory variable, and the following is the R code and output. Code for SAS is provided at the end of the notes. So looking here at the code, the first thing I do is I read in the data. This is very similar to what you would have seen, previously working in R. But notice to fit the model, I'm going to use GLM. So before, when we looked at linear models, you used LM. Now we use GLM. Now, an important thing in R when you're working in GLM, you do have to be careful how you are going to specify those categorical variables. So here I have specified them as factors. So you'll see that here in terms of status. Now you do want to be careful because how you define your categorical variables is going to depend on the interpretation. So at the end of the notes, when I actually go through the R code, there's some pieces that talk about that. And I show that you can actually fit a model 4 different ways. And then what you can do is you actually end up with the same information, but you have to be careful about how you interpret that information, and you can move between the models. So looking here at the output, notice that we have our intercept and our estimate for the effective age. And here we're going to let pi denote the probability that someone with age X survives. So looking at the output, we have the following fitted equation. And so notice these estimates are coming from right here in the R output. Now, you might say here, how do I know that status is being modeled as survived? And the way that I have this code written, it's hard to see that. And so what happened here is status is actually survived is the 1, and died is coded as the 0. But it's hard to see that from the output. And so that's kind of what that end piece where we look at the R code is going to look at. But continuing on here, notice we can use this to find pi hat. And then here the figure below kind of lets us see what's happening in terms of we're going to plot the logistic fit against age with the sample proportion superimposed on the plot. And so what we have here is our logistic regression fit. And here we actually have the proportions who survived, and each of the dots represents those observed proportions. So for example, if you went and you looked at the data, looked at everyone in the data set who was 30, you would see about 23% of those survived. Of those that were 40, approximately 70% survived. But then if we come down here to the 60s, we see for those that were in their 60s, very close to 0, and actually it probably is 0% of them survived. So the estimated odds of survival are multiplied by E to the negative 0.666, which is equal to 0.963 for each 1-year increase in age. And what that tells us is that for each additional year a person was, in age, that their probability of survival actually decreased by 16.4%. So now let's look at an example where there are multiple explanatory variables. So again, we'll consider a data set which involves the survival of the members of the Donner Party, but this time we're going to fit a model with both age and sex and then the interaction of the two. So again, here looking at the R code, you can see that I have fit an interaction model, and again, I've used that as dot factor for both of the categorical variables. Now here, looking at the R output, again, you get your estimates. And notice for the explanatory variables, it actually does give me which level it is fitting. So in this case, females are the reference, they're coded as 0, and male is coded as 1. Another thing to notice here, there's actually an extra line of code, I'll delete that out of your notes. But notice at the end that the number of Fisher scoring iterations is equal to 5. So we talked about, the getting the estimates via an iterative process in the last module, and you can see here that R is doing that. All right, so now let's take a look at interpreting the coefficients. The model coefficients are going to be more difficult to interpret directly because we fit a model with an interaction, and notice that they have to go through the link function before they're on the correct scale. So to help gain some familiarity with what the model coefficients mean, let's calculate survival probabilities for various kinds of people. So let's start out with calculating survival probabilities for males. So we're going to start out by writing our model. And so notice here in the model I have age, male, and that interaction term. And we could ask, what is the survival probability for a 20-year-old male? So remember that males are coded as a 1 in this case, so everywhere I have a male, I'm going to put in a 1, and for age, I'm going to place in 20. You've seen, we've done this several times before, with linear regression, a very similar process. So here, we get down to here, and we get our estimate, or we get really what the model is, not the estimate. We get the model for a 20-year-old male. So then we can look at our output and plug in what those values are equal. And notice that is going to give our estimate as negative 0.3312. But we're not interested in nu hat, we really want pi hat. So again, we're going to transform that, recalling that that is the transformation we want. Using our estimates, we get an estimate of pi hat is equal to 0.418. So a 20-year-old male in the Donner Party had a 41.8% chance of surviving. By a similar calculation, a 40-year-old male had a 27.3% chance of surviving, and a 60-year-old male would have a 16.4% chance of surviving. So next, let's look at females. So we can do the exact same thing, but remember now, females are coded as 0 because males were coded as 1. So everywhere we have a male, we're going to plug in a 0, and we're still interested in an age of 20. So now we have the following model for a 20-year-old female. Using our output and our estimates, we get the following. But again, we're not interested in nu hat, we're interested in pi hat. So we get the following for pi hat. So what this tells us is we have 96.7% for a 20-year-old female. Further calculation would show that we had 37.4 for a 40-year-old female and just 1.2% for a 60-year-old female. To summarize the trend, young adult females had a much higher survival probability than young adult males, but their survival probability decreases much more rapidly with age, to the point where older females were much more likely to survive than older males. Probably much less likely to survive than older males. Now, how could we calculate those estimates by hand? And here I have hand in quotation because we're really going to use R to do it, but it's kind of a good exercise to see where these are coming from. So note for the binomial distribution, when we looked at the weight matrix, we had the following. And we could implement that iterative least squares algorithm discussed in the previous modules. And so here's what this would look like. So the first thing we're going to do is construct the X matrix. There is a function in R that will do this. It's called model.matrix. So here we're just defining our model matrix, our response variables, and then we need to define a vector to hold our beta estimates. And so here we're going to fit that interaction model. So we have, the intercept, the coefficient for age, the coefficient for sex, and then that interaction. And then we have that iterative least squares algorithm. And so you could go back and compare this with the algorithm that we saw previously, and you would see that it is the same. In particular, you could see right here, you've got X transpose times W times X transpose times W times Z, where Z is defined here. So this is that same, setup that you saw in the previous notes. And then what's going to happen is the output is going to repeat until convergence, and convergence is actually defined by this little function right here. And what you'll notice is you actually end up with the exact same estimates from page 5. You could go on to calculate the standard error, the test statistics, and the p-values, and those are included here for you to look at. Alright, so what about visualization? So the plots below are going to compare the linear predictor as a function of age and the probability of surviving as a function of age. And so as you can see, and this happens most clearly for the females, that the logistic regression produces fitted probabilities that take on the S shape or sigmoidal curve, and we see that with this curve right here. This comes from the logit length function, which we've already demonstrated earlier constrains the fitted probabilities to lie between 1 and 0. And so you see the 1 and you see the 0 here. Once again, we see the utility of the length function. It allows us to obtain a nonlinear fit from a linear model. So linear regression is still the best linear unbiased estimator and is reasonable and in reasonable agreement for males, but the linearity requirement can lead to unrealistic estimates. So finally, all of the same questions when asked with linear regression about the systematic part of the model are still relevant to GLMs. For example, we have assumed a linear effect. Is this reasonable? Perhaps the probability of survival is low for young adults and elderly, and it maximizes in middle age. So including a quadratic fit for age in the systematic component of the model, we see that there may be some justification for this idea. And you can see that here in these plots. All right, so the last piece of the notes here, these are what I was talking about, the R code and the SAS code. I'm going to let you look through these on your own. You should be able to run those without issue. But the big thing that you're going to notice in each of these for both R and for SAS is I talk about it's important to know the levels of the variables when fitting the model. And so in particular, I'm going to show you that for the Donner Party example, you can actually fit 4 different models, and then you can use those to find those probabilities of that probability of survival for a 20-year-old male. And depending on which of the models you fit is how you're going to go about that. And you'll notice that the algebra that's here would be exactly the same thought process or argument is what we did here, where we started with the model and then we figured out what that survival probability would be for a 20-year-old male. So how you actually get to the model for the survival of a 20-year-old male will depend on how the model is specified here. So for example, if we specified the model in terms of females, we would want to have zeros here.